All right, picking up where we left off last class with mass percent. We did this example about mass percent. We were calculating the mass percent of a salt solution. Remember that a solution is something dissolved in another thing. And in this case, our solution was sodium chloride. That's our solute. It's the solid. It's also the minority component. And that was in water. So it's an aqueous solution. And water there is our solvent. And we used our formula mass of solute, that's the mass of the sodium chloride, divided by the mass of the solution. When you add the sodium chloride into the water, it doesn't just get vaporized or, it doesn't get Thanos snapped out of existence. It's still there, it's in the solution. And so we have to add the mass of our sodium chloride to the mass of our water to get the mass of the solution. And then we multiply by 100% because it's a percent, mass percent. And we got 3.46% sodium chloride. There are some other commonly used units that we don't use but are used in the real world. Parts per 100 is the same as percent. So 1 over 100. And parts per million is the number of grams per 1 million grams of solution. That's commonly used. You'll often see like pesticide in field water runoffs, for example, might be in parts per million or parts per billion. Sometimes things in your blood might be measured in those as well, but I think they use like nanograms per deciliter instead. But these are also common units in the solution and chemistry world. So you'll sometimes see those. If we want to use mass percent in calculations, we can use it as a conversion factor if we're given it. The key is remembering to write it as a fraction. So 34% mass percent can be rewritten as 34 grams of solute per 100 grams of solution. You could also write it as 0.34, which would be the same as 34 divided by 100. So as a ratio, it would be 0.34 grams solute to 1 gram solution. It's the same as how it's written here, just in a different form. I'm not super great, I feel like, at explaining mass percent because my brain just like does it, and I haven't figured out like how to explain it really well, unfortunately. So if you're confused, my Applebee's. All right, so an example, how much sucrose in grams is contained in a certain amount of a soft drink? That is 11.5% sucrose. We're going to assume that it's slightly more dense than water. So we've got our volume of solution, and we've got a conversion factor. We are also given a percentage that's also going to be a conversion factor. To start, we should figure out what this milliliters is in grams, since we're doing mass percent stuff. So 355 milliliters. We can multiply by 1.04 grams per milliliter. So the milliliters is on the bottom. That will cause them to cancel out. So then we're left with grams. And this is grams solution. So 369.2 grams of solution. Our formula for mass percent was mass percent equals grams solute over grams solution times 100%. So one way that we could use this is we rearrange this whole thing. We have the grams of solution. We have the percent, and we're trying to find the grams of solute. So that would be one way to do it. If we do that rearrangement, we'll get grams solute equals mass percent over 100% times grams solution. So that means we're going to convert this mass percent into a decimal form. That's the dividing by 100%. I wrote it that way for a reason. So that'll end up being 0.115 times our grams of solution, 369.2 So in our soda, whatever beverage we choose to drink, we've got pink, wrong color. There we go, 42.5 grams sucrose. It's kind of a lot. Questions? Yeah.
Knowing the density help us in the equation?
We can't solve it without the density. We could estimate it without the density because it's a water solution. We could also just get the mass of the soda. We would have to, pour out the can of soda to do that. Presumably, we would have had to do that to get the density, but this just gives you more things to do. Other questions? All right. Solution concentration also has the much more popular units of molarity. We've seen molarity before. It's shown up on a couple of solutions in our class, in our lab. We've seen this capital M. So molarity, capital M, or uppercase M, is moles solute over liters solution. Big M equals moles over liters. One of the reasons that we're specifying and pointing out that it's liters of solution here is because there is another unit of concentration that we'll talk about later that is not solution on the bottom. That is a much dreaded, much feared, much hated unit. I just don't like the way that it sounds when you pronounce it, the way that it feels. So we're all going to do that together when we get there so that you can experience it too. So one of the ways that we'll often use this, it sort of is reminiscent of our density. So some students like to do, just like with density, where density is mass over volume, you can do the little triangle thing. You can do the same little triangle thing here. Why am I drawing it the weirdest way? Because. So you can do the same little triangle trick. If you're familiar with the triangle trick, congratulations, you can use it here also. That might simplify things for you, but I don't use the pyramid scheme. But if that works for you, then go for it. Okay, when we're making things up to a specific molarity of solution, because usually we have a target molarity solution that we're trying to make. So if we're making a solution at a specified molarity, you put the solute into the flask, and then you add water to the desired volume of solution. This is because the solute has volume. It takes up space. If you get the volume that you want, say you want 5 liters of solution, you get out your 5 liters. You're like, great, I've got exactly 5 liters. Now I'm going to add in my kilogram of salt. Your solution level is going to come up, and now you no longer have 5 liters. You've got maybe 5.2 liters, and your concentration is going to be wrong. It's going to be lower than you intended it to be. So here's a set of steps that you might use that somebody put together. So you'll get your balance. You'll measure out your solid, this yellow powder, whatever it is. You'll dump that into a volumetric flask. A volumetric flask is a cool piece of glassware. You can use a volumetric flask for measuring one volume. It only works for one volume. If you want to use it for a different volume, you're sad out of luck. Go get a different flask. So for example, this might be a 1 liter flask. So if we fill it up to this line on the neck of the flask, that's 1 liter plus or minus maybe half a milliliter. It's like super, super accurate, way better than a graduated cylinder. So we're going to add it to our flask. We'll add some liquid into it before it gets up to this neck of the flask, because at that neck of the flask, it doesn't stir very well. So you'll fill it up so that the big bottom part is sort of full. You'll shake that around, get it nice and dissolved, and then you can fill it up the rest of the way, usually with like a wash bottle or a beaker, because you don't want to go over that line. If you go over the line, you've got too much solution, your volume's a little bit bigger than it should be, and so your concentration's a little lower than it could be, and you have no idea how much you're off by, because it's only good for measuring that one volume. I had some experience where I would have to make up like 15 of these in volumetric flasks like this, and that was always, I hated it, because you just have to get it like perfect every single time, 15 times in a row, or you like have to redo it. So that was always so fun to do every week. So you look and see that it's at the right thing, and then congratulations, you have the desired concentration of your solution. We aren't going to be doing this, but this is how you do it. So if you eventually down the road get to making your own solutions, you'll hopefully have flashbacks to this. And you'll remember in a moment of extreme clarity, oh, I remember what to do. I know how to do this. Or not, lab tech will help or whatever. All right, calculating molarity. We want the molarity of a solution made by putting 22.4 grams of HCl into a beaker and diluting that up to 1.56 liters. Why are we starting with units of grams? Because it's something we can measure. HCl is like a little bit of a weird one, but like this was sodium hydroxide comes in solid pellets, and so you can easily measure out a solid pellet on a balance. And you can't as easily just get magically the number of moles. So we'd measure out the grams. We've got 22.4 grams HCl. What are the units that go into molarity? Who remembers?
Grams.
Moles over liters. Big M equals moles over liters. So that means that we need moles and we need liters. We have liters. We were provided liters. That's pretty easy to measure. So we already have the liters. We need the moles, and we're starting with grams. Can we get from grams to moles? We sure can. What do we use to do that? Molar mass. Do we multiply or divide by our molar mass? We divide. So 35.45 and 1.008 to get our molar mass. Okay, so 22.4 divided by that number, we get 0.6144 dot 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 moles HCl. We take that number with all of its dot 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 decimals, and we divide it by liters. And we put that into our calculator. We get 0.394. What are our units? We can write moles over liters, but sometimes when two units come together, a special thing happens. In this case, we can turn it into capital M. And also HCl. It's just as accurate, though, to write moles over liters HCl. That's also correct. And this is a helpful trick for those of you that like to do dimensional analysis, look at the units and figure out what you're supposed to do. Capital M molarity is equal to moles over liters. We have that up here in our formula. Right? So anytime that you see this capital M, you can substitute in moles and divide it by 1 liter. Or you can do the pyramid scheme thing. That also works. Questions about that calculation? This is our new avocado toast, basically. It's bread and butter, but updated for the newer generation. Okay, so the way that we would read this, the way that I would read this, 0.394. How do we read the capital M? Molar. And I'm not going to write out HCl because I don't know how to write that out. But the big part of this is that capital M we read as molar. Like molarity, you just chop off the itty. A convenient thing that we can do with molarity is use it as a conversion factor between the two units that go into it, moles of solute and liters of solution. This is like molar mass, but for solutions. It occupies the same sort of like job title role, whatever you want to call it. It works in the same way as molar mass, but for solutions. So let's say that we have a sucrose solution, a sugar solution. We've got 1.95 liters of 0.781 molar sucrose solution. And we want to figure out how many grams that is. We are going to start, I'm going to start with liters. Secretly, molarity is 2 units, moles over liters. We can always swap in moles over liters for molarity. And so I'm going to choose to start with the thing that's got 1 unit. You can start with either of them, it doesn't really matter. I like starting with the simpler unit though. So 1.95 liters times our conversion factor of molarity. The liters is on the bottom in molarity, moles over liters. So we're going to multiply. That way our liters cancel. And this will give us moles sucrose. If you do the little pyramid scheme thing, look, a more normal pyramid, you would get the same thing. So we're finding moles, so you multiply molarity and liters. Gets you the same steps. So they both work. So in this solution, we've got about 1.52 moles of sucrose. And then we need the molar mass of sucrose. Which is 342.297. And if you're really confident that you can calculate molar mass correctly every single time, I'm going to let you in on a little secret. Google will tell you the molar mass, so you can just Google it. If you're not really confident, Google won't tell you the answer. Don't try it. Question?
How did you just find the molar mass of sucrose?
I put it in my calculator really fast.
Right, but what did you do in your calculator?
Yeah, so I did for carbon 12 times 12.011 plus 22 times 1.008
So we'll be provided that, right?
plus, not necessarily.
Oh, okay.
You're still expected to know how to calculate molar mass. It will show up on the final, 100%. Yeah, so I'm fast with the calculator. Not to brag too much. Right, so then we multiply. And this solution has more than a pound of sugar in it. 521 grams of sugar. You would not be able to measure that out on the scales that we have in lab because they max out at like 220 or something. You have to do this in batches or get a different scale. Questions about the process? So this is just doing that same sort of calculation with molarity, just in a different way, different application. Yeah, in water. All right, one for you to try. How many liters of a 2.25 molar copper sulfate solution, copper 2 sulfate solution, contains 55.8 grams of copper sulfate? Okay. What are we finding?
Liters.
Liters of copper sulfate solution. We're given molarity and grams of copper sulfate. Anytime molarity comes up, you should be thinking big M equals moles over liters. So one thing that we could do is swap out that big M for moles over liters. We could also rearrange this big M equals moles over liters. Since we're looking for liters, we want liters on a side by itself. In this case, that'll end up being us swapping liters and molarity. So liters equals moles over molarity if you did your little triangle scheme thing. If we're finding liters, we look at the other two things, moles over molarity. Voila, there it is. So what we're going to do is moles over molarity. We have molarity. Do we have moles? We do not have moles, and so we would have had to calculate that. I wrote out the calculation for the molar mass. We're going to divide by that to get moles. It'll be about a third. So 0.349 dot 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 moles copper sulfate. So if we plug that into our rearranged equation, that would look like this. 2.25 moles over liters on the bottom. So the moles will cancel. The liters gets flipped up to the top. For those of you that were very concerned about the way the units work out, I know I was. We get 0.155 liters copper sulfate solution. Questions about any of that work? A reason that we might do this calculation is if we want a 2.25 molar copper sulfate solution. For some reason, we just need some, and we have 55.8 grams. We could figure out how much volume, what our final volume of that solution should be. So this would be the most amount of solution that we could make with this amount of grams. So maybe we would need to order more or call over to a lab friend who has copper sulfate and get some from them to borrow if we needed more than this amount of copper sulfate solution. We also talked about different types of equations last week. One of them was the molecular equation. That's the one that we've been used to looking at. What were the other two that we learned about last time? In molecular, they're shown as neutral species. That's not how they actually exist in solution. In solution, they exist as, starts with an I, ions. So we had two different types of ionic solutions or equations. We had our complete ionic equation showing all of the things that are in the solution. And then if you take out the ones that are the same on both sides, toss those away, that's our what ionic equation? Net ionic equation. I just saw ion concentrations. I thought maybe jog our memory about that. Okay, the concentration that we talk about for talking about concentrations of solutions is the concentration of the molecular solute. And that's not actually how it exists in the solution. If it's a molecular compound, if it's something that stays intact like sucrose, it doesn't break into little parts into ions, then that's accurate. So if we have 0.5 molar sucrose solution, for example, that is actually 0.5 moles sucrose per liter. So for molecular things, things that have covalent bonds, that's actually how they exist in the solution. If we're talking about ionic solutes, the concentration for the ionic solute reflects before it was dissolved. So our example here, if we have a 1 molar calcium chloride solution, that means we took 1 mole of calcium chloride and dissolved it in 1 liter of solution. It's not going to contain 1 molar of each of the ions, however, not in all cases. So it's going to contain 1 mole of calcium per liter, because there's a subscript of 1 that is implied. But we have a subscript of 2 for our chloride. So there's actually going to be 2 moles of chloride per liter because of this 2 subscript. If you want a way to calculate that out, we've got a 1 molar calcium chloride solution. There are 2 chlorides for every 1 calcium chloride. So that would be a 2.0 molar chloride concentration. It works for calcium chloride since it's a strong electrolyte, so it completely dissociates. Questions about that? Confusion? Yes?
Could you re-explain that part?
So the reason that it's a 2 molar concentration of chloride is because in each of these calciums, the calcium, when it dissolves into solution, is going to break into 1 calcium, and it's going to break into 2 chlorides. Since there's 2 chlorides for every calcium chloride, then we have to double the concentration to account for 2 chlorides being there. It's still a 1 molar calcium chloride solution, but if we're talking about the chloride part specifically, we have 2 moles for every 1 mole of calcium chloride, so 2 molar instead of 1 molar.
And you got that ratio from
The subscript.
from the subscript.
Yeah. We've done the subscript counting stuff before. So this is sort of review we're building. We're adding on. All right, determine the molar concentrations of calcium and chloride in a 1.25 molar calcium chloride solution. For those of you quick with mental math, you may already be done. All right, so starting with the concentration of the neutral species before it was dissolved, we're going to do stoichiometry is basically what this is. So we're going to look at a ratio of one thing to another thing. In this case, we're looking at the ratio between calcium chloride and either calcium or chloride. Let's do the calcium first. I think it's easier. How many calciums do we have in one calcium chloride?
One calcium.
We have one calcium 2 plus in every one CaCl2. So the concentration is going to be the same. Our solution is a 1.25 molar calcium 2 plus solution. To calculate it for chloride, we can do the same set of steps. How many chlorides, Cl minus, do we have for every one calcium chloride? 2 Cl minus for every one CaCl2. So it would be a 2.50 molar Cl minus solution. Question?
I'm assuming we just divided 2 by 1, right? 2 CL. Okay.
Yeah.
How did we get 2.5 out of 2 divided by 1? Wouldn't that just be 2?
The 1.25 in the front. 1.25 times 2. I just wrote it a little differently than I normally do. Other questions? Cool. You may have heard that the solution to pollution is dilution. That's not actually true. It does sound nice, though, so I like to say it when I get the chance. So solution dilution is not complicated. There's a very easy formula that we can use specifically and only and never for anything else, only for solution dilution. So the reason that we're talking about solution dilution is because it's convenient to store solutions in high concentrations because you can always add water and dilute it down, and now you've got more solution. You've got a lower concentration solution. If you wanted to reduce the volume, get rid of some of your liquid from your solution, you would have to concentrate it. How would we remove the liquid from a solution? We could heat it up. Not everything can be heated. Sometimes things degrade when you heat them up. We could dry it. It's dissolved, so we can't filter it. There's special chemicals that we could use maybe to remove some of the water. We could do it at a lower temperature by reducing the pressure so that it boils at a lower temperature. But hopefully the thing that you're taking away is it's difficult, right? It's not just add water. It's not like dehydrated water where you just add water and now it's there. It's more complicated. So it's easier to dilute down, and it also takes up less space. Yeah, you can buy dehydrated water in cans.
There's actually dehydrated.
Yeah, you just add water and then.
Funny.
Thank you. So it's easier to dilute than to concentrate. So we'll take our high concentration stock solution, we'll pull a small bit of it, sometimes called an aliquot. We'll mix that up with a different solution volume, and now we've got our desired concentration solution. And here's that equation that I was talking about that we're only going to use for solution dilution and we're never going to use for anything else because you'll get things wrong. I promise you'll get things wrong. I'll make it so that you get things wrong. So solution dilution, we can use this very convenient equation, M1V1 equals M2V2, where the capital M is a molarity and the capital V is a volume. The way that this works, right, is molarity equals moles over liters. And so if we take moles over liters and multiply it by liters, then that's a number of moles. So in this M1V1 equals M2V2, we're saying on the left side we've got moles in one solution, and on the right side we also have moles, just in the different solution. But the number of moles is the same. When we dilute something, we're adding water in. We're not changing the other substance that's in there. We're just changing kind of like how it's dispersed. It's like if we took everyone in this class and we went to like a big lecture hall at Fresno State and we put everyone in the lecture hall, right? We could spread you all out. It would still be the same number of students, even if we spread you out into a really big room, or if we crammed all of us into like a clown car, right? It would be the same number of people regardless of the situation. That's what we're doing with M1V1 equals M2V2. So that's why it works. And we're going to use this only for dilution. We're going to learn about solution stoichiometry. It's tempting to want to use this for solution stoichiometry. I promise I will make it so that you miss points if you use this on a thing that's not solution dilution, but it's great for solution dilution, so we're going to use it there. I'm saying it so many times because no matter how many times I say it, somebody's going to do it. Somebody's going to try me. I think I had people on my 1A, one of my exams, with solution. They used this solution dilution thing on one of the short answer questions, and I just gave them 0 points because I told them not to.
For that question or for the whole thing?
For that question, not for the whole thing. Yeah. Canceled just a little bit, you're not completely canceled. Okay, again, this applies only to solution dilution, and it doesn't work for stoichiometry. I'll show you why it doesn't work for stoichiometry later. So the insidious thing about this is that it does work sometimes for the numbers reasons. So it will work if you have a 1-to-1 ratio. If you don't have a 1-to-1 ratio, it doesn't work. There's a way that you can modify it so that it does work. I don't understand it. You could use it maybe, but I don't like it. Another lab safety note. Generally, when we're dealing with acids, the way that acids and water mix produces heat. And so when you're adding water to acids, or when you're diluting acids, the acid part dissolving into the water is the part that produces the heat. And so if you add a little bit of water to a bunch of acid, that's going to cause that acid to go crazy, go nuts, go other things that you might say about going wild, and produce a lot of heat. And that could cause your solution to spontaneously boil. And boiling acids is generally not a good idea unless you're intending to boil acids, because it'll produce acid vapors. And if you breathe the acid vapors in, then you get acid burns in your lungs, because it probably condenses in your lungs. So it's like a whole lot of bad things happening all at once. And so you always want to add the acid to the water, because the acid part produces the heat. If you add it to a bunch of water, the water can absorb that heat and it doesn't get super warm. So never add water to concentrated acid solutions. It's bad stuff. There were a couple people in our lab last week when we were adding water to acid, but like in specific amounts and for reasons. So we were doing that. Don't do it generally. We were doing this, and some people noted, oh, my eudiometer is really warm, because we were doing this. Fortunately, it was a small enough amount of acid with a large enough amount of water that nothing bad really happened. And the phrase to remember here, acid to water, like you, fuzzy river mammal. Sorry. Otter. Acid to water, like water, or ought to. That's the memory phrase for this. All right, we're going to do a solution dilution example. We have a 6 molar nano solution, and we want to make 0.442 liters of a 1.2 molar nano solution. This is somewhat reminiscent of our simple gas laws stuff, like Boyle's law, for example. Boyle's law, very, very similar. So our equation that we use solely for solution dilution is, again, M1V1 equals M2V2. If we had a P there instead, right, that would be Boyle's law. So M1V1 equals M2V2. And just like with our simple gas laws, the important part here is that we don't get our numbers mixed up. We've got two capital M's, 6 molar, 1.2 molar. Which of those goes with 0.442 liters? Does our volume go with 1.2 molar or 6 molar? It does not go with the 6.0 molar. It's 0.442 liters of a 1.2 molar solution. So it goes with a 1.2. So in this case, I called 1.2 molar M2. So that means that V2 is 0.442 liters. If you get them switched, that's like the one way that you're likely to make a mistake here. Or if you screw up the algebra. That's another way that you could do this. So we're finding the other volume, which is V1. So we want to isolate V1 by itself. V1 is going to be M2 V2 over M1. We can tell this is going to work out with the correct units because we've got a molarity on the top and a molarity on the bottom. Those have the same units. Those will cancel out. We've got a volume on the top, so that means that we're going to have volume units for our V1. If you somehow ended up with all of them on top, right, your units won't cancel out. So that could maybe be a way you could check. So our M2 1.2 molar times our V2 0.442 liters divided by 6.0 molar. So the volume that we would be starting with, 0.0884 liters. Of that 6 molar solution. So we would take this 88.4 milliliters, we'd put that into a container, into something that we can measure this volume, and then we would dilute it up to this 0.442 liters, and then we would know that our concentration is 1.2 molar. questions? Here's what that might look like. We already talked a little bit about volumetric flasks. We're seeing them again here. So you would take your liquid, possibly from a volumetric flask. You would pull it out with maybe a volumetric pipette. Volumetric pipettes, like volumetric flasks, are great at measuring one volume. They only measure that one volume. It's kind of the same concept. So we'd use that to pull out the correct amount, add it to another flask, and then you can fill it up with water to whatever the mark is on the flask. And now you've got your dilution. One of the troublesome things about doing these dilutions is that they only make volumetric flasks in specific sizes. They only make volumetric pipettes in specific sizes. And so it's a little bit of what size flasks can I use to get the concentration that I want, or how can I adjust my... It gets complicated. You don't have to do this. I didn't like it. And I ain't ashamed to say it. Okay, so that's for solution dilution. We also have solution stoichiometry. Can someone name an equation that we're not going to use for solution stoichiometry? That's right, M1V1 equals M2V2. We're not going to use that here. But we will learn some other things that we can do instead. When we're doing reactions with solutions, things that are dissolved, aqueous, reactant, and products, it's not very helpful to say, here's how many grams of the solute we need, because we can't directly measure it. It's dissolved in a liquid. We can measure out the amount of the solution, but we don't know the density. We could calculate the density, but then it's like it would be a whole thing. And so it's a lot easier to specify in terms of volume, usually in liters or milliliters, and concentration with molarity. Usually we'll know the concentration or have an approximate knowledge of the concentration. And we can use those to calculate the number of moles. Since M times L equals moles. So we can figure out how much of the reactants or the products we have, and then use stoichiometry, stoichiometric coefficients, aka ratio, from our balanced equation to convert to other things in the reaction. Let's see what that looks like. So a general solution map. This is just one way that we could do it. We've got a volume of some solution A. We can convert from volume to moles using our molar concentration. This is like going from grams to moles, where we use molar mass. We hopefully remember how to do that. You will need to know how to do it, certainly for the final. And then we can go to moles of a different thing. So this middle step, the stoichiometry step, is the same as how we've always done it. That's not new. But then from moles, since we're dealing with solutions, we could go to molar concentration, molarity, or to volume. And that's similar to going to grams, again with molar mass. So up top, what we've done, what we're doing below. So we're just changing up the steps a little bit. Instead of grams, we're using volume, or instead of mass, we're using volume. Instead of molar mass, we're using molarity. And you can switch volume and molarity for either or both of those first and last steps. As an example, using that reaction scheme, what volume in liters of this concentration sodium sulfate solution will react with this many milliliters of this concentration of barium chloride, given the following balanced chemical equation. Where are we going to start? Any ideas? Where are we going to end? We're finding liters of what? Sodium sulfate. That is not the same balanced equation, but that's all right. Well, that's quirky and fun. All right. BaCl2, Na2, SO4. Who did this? Who put these slides together?
Couldn't be.
There we go. I think that's correct and balanced. All right, we're finding liters of sodium sulfate Na2SO4. Do we have anything else related to Na2SO4?
500.
We've got this concentration. What can we use that for? Yeah, M is moles over liters. If we're finding liters, then that means that we would need what to get to liters? Moles. So before we get to liters, we'll need to get moles Na2SO4. And what's the chemical that we're starting with? Barium chloride. Can we get from barium chloride to moles of barium chloride to moles of sodium sulfate? Darn tootin'. We're going to use that ratio from the balanced equation that I wrote out. Do we have what we need to find moles of barium chloride? We do. What are those things? Yeah, milliliters and molarity. So to get to moles using molarity, what do we have to have? Capital M is moles over liters, right? So we need to have liters here. we can get to that from our 275 milliliters. Another way that you can figure out, if you wanted to figure out where to start, we have two things for barium chloride. That's the thing we're starting with. And anytime that we've got liters and molarity or moles and molarity, we're going to find the other thing. We're always using molarity as a conversion factor. Occasionally it's our target. Usually we're using it as a conversion factor. So we're starting with this 275 milliliters. We need to convert that to liters. 1 liter contains 1,000 milliliters. So 0.275 liters BaCl2. What is capital M equal to?
Moles over liters.
Moles over liters, so we can multiply. Because that'll put liters on the bottom, so liters cancels. You can do the triangle thing, you can rearrange. There's other ways to get that. So that's our moles of barium chloride. What's our ratio of barium chloride to sodium sulfate? They're 1-to-1. So as a formality, we're putting in the 1-to-1 ratio just to show that we're canceling our units, just to show that we care. And now we've got some number of moles of sodium sulfate. How do we get from moles to liters with molarity? Multiply or divide? Divide by moles over liters. The moles cancel, and we get out our answer. It is 0.1375 or 0.138 liters sodium sulfate. Questions?
So basically you said that just to start as a hint with whatever has two numbers to that, like barium. Always go for the one that has just good sets of information, two information.
99% of the time, probably, yeah. If we forgot what I've been harping on, and we were looking for a volume of our sodium sulfate, and we didn't get things confused, calculating for V2, that would be M1 V1 over M2. This liters is our V1. This molarity is our M1. This 0.500 molar is our M2. So this is one of those instances because we have 1-to-1 ratio. This solution dilution equation gets us the correct number.
But don't do it that way.
It only works if it's a 1-to-1 ratio. If it's a 1-to-2 or a 1-to-3 or a 2-to-3 or any other combination thereof, you will get the wrong answer.
So you will make sure that we don't have 1-to-1 ratios.
You will definitely not have a 1-to-1 ratio at least sometimes. Yes. Questions about stuff today? Don't worry, we'll get to those gross, sick, twisted units that I was talking about earlier. They're not really that bad. Later.